Moving on to density now. We used a density meter utilizing the oscillating YouTube method. Simply the way this works is that we have a small sample of small sort of volume of fluid. We're talking less than a milliliter in this case, and we draw that into a hollow U-shaped tube, which is then set into mechanical oscillation using the pulse excitation method. Now, the key principle here is that the frequency at which that tube oscillates depends on its mass. And since the volume of the fluid inside is fixed and it's known, the instrument can then calculate the density directly from that oscillation frequency. It's quite a fast, precise measurement. And as the tube itself is thermostated, it's quite good for precise temperature control, again, allowing us to get density over a range of different temperatures. And again, with viscosity, 2 runs per sample at each temperature was done here. And looking at the results, the pattern is going to be as expected. You get a steady linear decrease in density as you increase your temperature. As you're warming up your fluid, it expands and the same mass now occupies a slightly larger volume, so the density drops. In terms of the differences between the samples, optical CM had the highest density we can see across this whole temperature range, and the other samples sat below it. And again, as with the viscosity data, there was no meaningful differences between the fresh and in-service competitor products. Now, beyond being a value required for freedom of merit calculations, we also used it to feed directly into the coefficient of thermal expansion calculations, which we're going to come on to next. But density has further practical relevance too. It feeds into things like tank design, as a denser fluid means a heavier filled tank, and also feeds into things like pump design, as if the fluid is pumped from the bottom of the tank, it has to work against the full height of the liquid above it.